Okay.
Yeah.
Okay, am I audible now?
Yes, sir. Yes.
Is it okay?
Yes. Yeah. Yeah.
Okay,
Yeah.
yeah, yeah, yeah. So the focus of uh, wind power or wind turbine generators in this presentation is of course on microgrid. But I will start with large machines. What are the machines and how are they for a general uh, introduction? I do not know, but all the participants are aware with the technologies. That's why a basic introduction of the machines or the technologies, and then we will proceed to the future versions and the future developments are required, or rather, the recent developments which are happening across the globe in wind power onto the microgrids in grid connected, and more than that, in a standalone, that is islanded mode of operation. As the organizers told you, you can post your comment questions in the chat box. Once I complete it, I will come to that. At the same time, I will suggest that if uh, someone feels to raise a question during the presentation, I don't object to it. You can switch on your mic and put the question on, because asking a question at the right time can be more useful. Yes, this is a wind turbine generator, but it's the single machine of 2.1 megawatt, 1100 kilowatt capacity. You can see the environment's a very rural environment, but it's connected to 110 kV grid substation to the transmission grid. As usual, as is the common case, this is producing power, selling to the grid, to the utility. That's the state electricity boards. And then along with mixing with the regular contingency, this is being sold to the customers. This is the present practice. When we discuss the wind turbine generators, in fact, the discussion should start with the characteristics of the turbine. Electrical engineers, when they discuss, when they teach and learn electric power generation, power plants, less attention is given to the turbine performance and turbine characteristics. But then that won't suffice in the case of wind turbine generators, because there is a lot to do on that part. It doesn't mean that one has to be very familiar with the aerodynamics of the turbine, yet a basic understanding is good. I'm not going to present the principle of the turbine or the aerodynamics, but just the characteristics, how these characteristics influence the performance of the generator, and whether in grid connected or in islanded mode, why these characteristics are quite to be considered when the power engineer or the power electronics engineer plans a control or executes a control, any control, the electrical side. You are seeing, uh, many will be knowing again. Still, let me have a review because I'm not sure whether everyone is aware of it. This is the characteristic of the wind turbine generator. It's a plot of power coefficient versus tip speed ratio, as is written here. Power coefficient means the efficiency, power conversion efficiency of the turbine, and tip speed ratio is defined here, lambda, omega into R by V, where omega is the angular speed at which the turbine rotor is rotating. It's radians per second. And capital R is the length of the blade. See, this is a turbine photograph is here. This is the length of the blade. This is capital R, means of the swept area, the radius of the swept area, that is R. And in the denominator, the small v is the wind speed. So it's called the tip speed ratio because the numerator is the tip speed, the speed, linear speed at the tip of the blade. Angular speed into that radius, that will be giving you the speed at the tip of the blade. that divided by wind speed. So as you see this curve, it shows that this maximum efficiency happens somewhere between on a middle value. The usual range of operation of the speed ratio for a wind turbine uh, is say up to 15, and usually the design lambda or the optimum lambda will be around 7 to 9. In this case, you are seeing that when the lambda is 7, then it's giving maximum efficiency. That's called the maximum. The CP, power coefficient, is called CP. Uh, it has a theoretical limit, 59, about 59%. That is because when the wind passes through the turbine, then it gets split um, across the blade of the turbine, and there is a lift force and a drag force coming. The design is such that a drag force is minimized, and with a lift force means that is will be acting like this. With that, it rotates. So with that lift force, that the power and produces a torque. With that, it rotates. That's the power. So that after passing through the blade, the wind is further proceeding. Now the power in the wind, that is because of the kinetic energy in air motion. This energy is partly uh, taken by the turbine, converted by the turbine, but it cannot be fully extracted from the wind because some kinetic energy has to be left with it. Then only the flow can continue. And the flow has to, like any other power plant, uh, you say a hydropower plant, a thermal steam power plant, a gas power plant. In all these cases, the turbine is working in a fluid. So here also, it's a fluid. It's different. It's different from gas slightly, much different from water and steam. The density is quite different. The density is much less here. Otherwise, the flow has to continue, and that is why the full extraction of power is not possible. So theoretical limit is 59%. Practically or commercially, 50% of power coefficient uh, made available in the large turbines available in. Yeah. So this is the characteristic of the turbine. So the turbine, when it operates, it may be operating at a different points of operation. The operating point will be varying usually. In the start, for very low wind speed, it may be around here, and then it moves like this, and finally, when usually a turbine generator works in a wind speed range 3 to 4 meter per second is a minimum, a maximum of 25 meter per second. When it works at a high wind, that is 25 meter per second, this efficiency will be much less, 1 2% only. We need to limit it because quite a large amount of power is contained by a large speed. All that power cannot be taken, extracted. Maybe at a later stage, that part also we will be discussing. Anyway, understand that CP is continuously varying in the present state of the art machines, and the average CP will be around 20 to 28%. In fact, this power coefficient is not only a function of lambda, it's also a function of beta, which is a pitch angle. Now the turbine blade needs to have a pitch angle, like the fan. A ceiling fan is not a plane, no, the plate's in a horizontal plane, but that blade has an angle, that plane, that's a pitch angle. The pitch angle, if you vary, the characteristic also varies, especially the maximum value. One, the range of lambda operation that changes. Now the maximum value, um, CP max, that also varies. It is changed on both sides of the default design value, 5 or 10 degrees on either side, and it is varied. Both cases, as you are seeing in the graph, all the values are come down on. So that the usual design lambda, sorry, the pitch angle beta is around 5 to 7 degrees. must be knowing that the power in the wind that is expressed as half rho a v cube. Basically, the kinetic energy half mv square. Its rate of change, that's power. If you derive it, it will come as a half rho a v because rho a v is the mass flow rate per unit time. What's the mass of air flowing through the turbine of a cross-section area, that is a swept area of capital A, and the wind speed of V, that is the power in it. This, when you multiply by the power coefficient, you get the power output of the wind turbine P, that G. And again, if it is coupled with the generator, electrical generator, then again, the efficiency of the generator, you have to consider eta G. Finally, we get this expression, power output for a particular wind speed V. Now, we have, as the state of the art in the market, two types of wind turbine generators that commercially people classifying as a fixed speed turbine generators and variable speed turbines. What do we mean by this fixed speed or variable speed? That I will explain here. After that, two types of turbine we discuss. We have seen those lambda, that is the tip speed ratio. Now here, if omega means angular speed, if that is not varying with lambda, varying with wind speed will be varying, the turbine operates the usual normal operation. With a change in the wind speed, suppose the angular speed, the shaft speed is not varying. In that case, lambda will widely. For example, the operation at the minimum wind speed will start here, and at rated wind speed it will be here, and the final the cutoff wind will be about wide variation lambda. The corresponding CP values, if you see, and if you take the average, that will be a low value. And suppose we are able to, or the turbine is able to vary its angular speed, the shaft speed, along with the speed variation. If omega varies with V, then variation in lambda will be less. If omega is proportional to V, what percentage variations are happening in the same variation, same percentage variation is happening in omega. In that case, lambda will be constant. And it gives a chance that if you can keep lambda constant at the design value, optimum value, then the maximum efficiency can be obtained. But this is not possible above the rated value, rated wind speed of the turbine, because at the rated wind speed, the turbine will be giving a power output. With that, the generator produces its rated capacity. Now, you cannot overload the generator. For that reason, for wind speeds above the rated wind speed, we need to curtail the power extraction from them. For that purpose, deliberately, by design, the CP is reduced. That's why above wind speed is more, as I told you, at the final wind speed, usually in the case of commercial wind turbine, this is 25 meters per second. At that wind speed, it will be around 1 to 2%. So above rated wind speed, we cannot maintain highest efficiency, but it's possible from the cutting wind speed, when the minimum wind speed up to rated wind speed, the wind turbine is able, it can be made to perform at maximum efficiency if lambda is maintained constant at its design value. And if we are not doing that, all these things requires a cooperation from the generator or a control of the generator. Then only the omega can vary. Because turbine speed that is coupled with a turbine is coupled with the generator. Turbine is free to operate at any speed. It doesn't have, it's not very stubborn as far as its shaft speed is concerned. Well, at that shaft speed and the corresponding wind speed, whatever is the lambda, according to the CP will be decided. But then the electrical generator is more rigid. You know that a 4-pole machine, whether induction or a synchronous machine, when at 50 hertz when it operates, the speed has to be around 1500. If it is synchronous machine, at 1500 it operates. If it is induction machine, it will be around 1500. Motoring mode, it will be below 1500. Otherwise, it will be above that. It cannot, if you want to reduce that speed, means you have to change either the frequency, but grid connected systems changes up frequency is not possible unless we make a synchronous link. Otherwise, we have to increase the number of. So usually, the generator is electric generator is rigid regarding its speed, and when coupled with the turbine, the generator decides the speed or the range of speed. For that reason, varying omega with the wind speed proportionately. It's not an easy task. Well, which generator, to what extent this can be done, we can discuss later. But for the time being, the purpose of my mentioning this is to tell you that there is, if we can control or if we can have a system, a combination of turbine and generator, where omega can vary with the variation in the wind speed, it is beneficial. Overall efficiency can be high. So systems where change in omega short speed over the entire range of wind speed is minimal, not significant. Such systems is called a fixed speed system, and UTG systems, wind turbine generator systems, where the short speed can considerably vary. It's called variable speed system. Now I can make the comment that variable speed wind turbine generators are more efficient than fixed speed wind turbine generators. This is proven in the field. In fact, commercially, the wind power generation, grid connected wind turbine generator are there from 1981, since the first one installed in California. Or if you are referring to India, in 1986, the demonstration machines were installed, but commercially from 1990 onwards, we have these things every year getting added. But in the 90s, till say up to 2005, 2006, almost all the machines installed were fixed speed machines. They're basically induction machine. You know that in an induction machine, especially the squirrel cage induction machine, the slip variation or the speed variation from no load to full load is very less. 3 to 5% slip only will be there. If you're considering very large machines, it's still smaller. But by design, we can increase it to some extent. Otherwise, the slip is small. For that reason, the variation in the wind speed is less. And if you look at this statement. In fact, I'll explain this with a large figure later. But otherwise, what is being shown here is a wind turbine coupled to a generator. That's an induction generator through a gear. So the purpose of the gear is to provide a low wind speed to the turbine and allow the generator at a high speed above that. Because the turbine, a large machine, these days we have wind turbine generators of very large capacity, very large size, and such large size machine, and that too at a hub height, more than 100 meters is going these days. Such a vast thing erected, the foundation requirement and the structural engineering design requirements will be extremely costly, material requirement also. So we cannot allow the turbine to run at 1000 RPM or 1500 RPM. That's why the gear is kept there. Now consider that the gear ratio is 1:50. When 1500 is the generator RPM, 30 will be 30 RPM will be the speed of the turbine. If that's the case, say for an induction generator with the slip, the usual variation in the speed of a 4-pole machine means from 1500, it has to be on the higher side, so it can go up to 1550 or 60, some 50 to 60 RPM. That will be the usual variation speed. This, when translated on the turbine side, you can see that the turbine speed is varying around 1 RPM or less than. Especially these days, the machine which I was showing the photograph in the beginning, that's a 2100 kilowatt machine, and its turbine RPM sorry, its gear ratio is is a 1:100. So with such a gear ratio, it's 12 to 15 RP. Um, in that range, the turbine will be working. So hardly any visible change will be there in the speed. That's why it's called a fixed speed machine. Whereas other cases, say some 30% slip, the 30% of 500 RPM, 1500 to 1500, 2000, that range, if the speed is varying, then it will be visible. That's called a variable speed machine. So the separation or the classification as fixed speed machine and variable speed machine has happened like this. And as I was telling you, up to 2000, 2005, only fixed speed machines we had, that is induction generators, squirrel cage induction generators were used in wind turbine along with wind turbine. After that, only the new turbines like the permanent magnet machines and DFIG, doubly fed induction generator, that is slip ring induction machine, were brought in. And with that variable speed machines, the production increased because of the higher efficiency, the profit increased. As a result, manufacturers are not making regularly squirrel cage induction based fixed speed machines are not made or supplied or even purchased or installed today. But machines installed in the past, they are still there. The life is 25 years roughly, but we have machines even above that. 1990, what we installed are still there. That means 30 years crossed, still those machines are there. Only those old machines are the fixed name machines, but recently the machines we are having are all variable speed machines. Yeah, this is the power.
So, sir, one
Of
question.
yes, yes, yeah, sure,
Sir,
please.
it's based on the previous slide.
Yeah,
So, it's regarding the tip speed rate. So, I
yeah.
see there's like an angular velocity, and the velocity of the wind. So, why isn't the angular velocity not proportional to the wind speed? Are there like any other factors which affect? It should be proportional, right? When the wind increases, the angular velocity also increases, if I'm not wrong.
No,
So why isn't
why
it?
should
Why is it? Yeah,
yeah? I'll tell
sorry,
you.
sir.
I'll tell you.
Yeah,
Now the speed is decided as a requirement to transfer the power. When two machines, a machine means a power converter. Wind turbine is a machine, and electrical generator is another machine. When these two machines are interconnected, so here the connection, the coupling, even though it is through a gear, any change in the speed on either shaft, there will be a proportional change. So you can consider that the speed change will be together. The turbine and the generator cannot have different speeds. It will be the same speed. Now, speed, if you look at, I hope you are an electrical engineer.
yes, sir.
Yeah. So you know that an induction machine, it's a slip, as I told you, is varies hardly 3% to 5% only from no load to full load. That means to deliver certain amount of power, there is a certain speed, rather slip is required. The slip torque characteristic of an induction machine
Yeah,
shows that to
yes,
deliver
sir.
a torque or
Yeah,
corresponding to a torque, there is a fixed slip, so corresponding
yes,
value slip.
yeah,
And the slip means there's a speed that omega, that is the angular speed and the torque together, that makes the power.
yeah,
That means for the generator or the motor, the induction machine, the electrical machine, that the speed decides at what power it is to operate. Agreed?
yeah, yeah.
Hello, I didn't complete this. This part is clear now. For the
Yes, yes,
induction
yes, sir.
machine, for the electrical generator, power is linked with the speed. Now you
Yes,
come
sir.
to the turbine characteristic, which I'm showing. It is telling exactly the same thing. Lambda tip speed ratio, that's also having the speed, the
Yeah,
omega in that. So the speed
yes,
is
sir.
linked with the power. For any machine, electrical
Yeah,
or mechanical, the speed is linked with the power. Now,
yes, sir.
when the turbine is extracting certain amount of power from the wind, that power needs to be transferred to the generator and then further to the load. Law of conservation of energy, that's
I
called
agree.
balancing, has to happen. So
Yes, sir.
the speed at which a certain amount of power that can be transferred by the turbine from the wind to the generator, and the speed at which this power can be taken by the generator and transferred to the load. Both the speeds should be the same.
Yes.
When I say it should be the same means I'm not forgetting the gear, but the gear is only making a fixed ratio. So the speed is rigid.
Okay.
So that means for every wind speed, the system will decide at what speed it has to operate so that power balancing is secure.
Okay.
Shall I repeat? For every wind speed, the two machines together decide. This is like if you simulate it through iteration, we decide this thing. Exactly. These
Yeah.
iterations are happening in every system for power flow equilibrium.
Okay.
Okay,
Yeah.
so for the generator is deciding that the speed that it requires, that change is hardly 3 to 5%. So
Yes.
the turbine speed cannot be different. There
Yeah.
also the speed change will be 5 to 3%. But you see what is
Yeah.
the change in the wind speed? The wind speed for no load at a zero output, the wind speed is around 3 meters per second. At a rated output, the wind speed may be minimum usually 12 meters per second, 12 to 15. So if it is 3 and 12
Okay.
means a 400% increase is happening in the wind speed. And what is the corresponding change in the angular speed? Only 3% or 5%.
3%.
So don't
Yeah.
think
Yeah.
that a change in wind speed requires a change in omega. It is decided by, this was my point which I was trying to give a few minutes back,
Okay.
the speed of operation. Shaft speed is decided stubbornly by the electrical generator. Interesting thing,
Okay. Yeah.
when the speed change is so, as we discussed with the induction machine and the turbine. The same turbine you detach from that induction machine and you connect with a synchronous machine and allow
Yeah.
to operate in a variable voltage, variable frequency operation. Means asynchronously you connect to the grid or you give a dedicated load so that with every time the power varies, the speed also has to vary, the frequency and voltage, everything varies. The
Yeah.
variable voltage, variable frequency operation. At that time, you will see that maybe the speed omega is changing. You can make it change proportional to the wind speed V. A large change in wind shaft speed will be happening there. The same
Okay.
turbine will obey to whichever generator is connected to it.
Okay. Okay. Yeah. Yeah.
Interesting.
Yeah. 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 Because I kind of misunderstood the concept, in which case, like,
Yeah.
I thought those two were like in proportion. Yeah. Thank you, sir.
Yeah, so this is a point actually we all need to consider. That's why I was telling you initially that the turbine need our should be our under our study. We should understand the turbine behavior. Then only we will know at what speed and what's the control required, how much we can control all these things. All the controls are required to be done, or most of the controls are required to be done on the electrical side. But
Yeah.
for that, an understanding of the power balancing with the turbine, mechanical machine and electrical machine is
Yeah. Yeah. Okay.
okay.
Thank you, sir. Thank
Yeah.
you so much.
So, yeah. Yeah. So now let me already I said partly, but still to consolidate data. Any machine, wind turbine generator, if you purchase, or if you are a researcher or a teacher, if you take it in the website of a manufacturer, every machine, every model of any manufacturer will be represented by a power curve. That is the power output for the wind speed. Power output of the generator plotted against a wind speed. This is called a power curve. Now this power curve has three rated wind speeds. As is shown in the diagram, you can see that this is called a cut-in wind speed, below which there will be no generation. This is called a rated wind speed, at which the generated power will be equal to the rated power of the generator, electrical generator. And then there is a cutoff wind speed, beyond which no generation is possible. And again, this will be interesting to understand why it is so. Cut-in wind speed, below that it does not operate, meaning the system, the power flow equilibrium we discussed just now, there the only thing we missed is the losses in the system. Each machine will be having some losses. As far as the turbine is concerned, some losses are there, or even otherwise it's not fully extracting the power from the wind. As I told you, the bed's limit. For that, part of the energy input, the power input, part of that is not taken. Losses are happening. And then in generator, there are electrical losses and negligible mechanical losses. All those things are there. So it should, in power input to the wind turbine minus its losses, that is its power output of the turbine. Then power output of the turbine is the input to the gear minus its losses is its output. Again, a generator has its power input minus its losses that will be its output. To get any useful output, I repeat, to get any useful output at the generator terminals, the input power should be having some value above the total losses in the system. So below the cut-in wind speed, the power in the wind is not sufficient to meet the losses. What all losses are applicable there, that magnitude will not be sufficient. That's why it is not able to give an output or not generating. Yeah. Now, before coming to rated wind speed, let us look at the cutoff wind speed. At cutoff, beyond cutoff wind speed, it's not generating. Why? That is, previous case I showed you the formula, the power in the wind that is proportional to cube of the wind speed goes on increasing. It goes on increasing, and it proportional to cube of the wind speed. We cannot extract all that power. Our system has some capacity. So we cannot extract all that power. So if it exceeds a certain limit, then we will have to stop operation. So the cutoff wind speed is where actually we decide that we will shut down the plant. We will stop the machine. We will not generate further. That is a cutoff wind speed. Now, the one interesting observation you might have made that the power in the wind is proportional to cube of the wind speed. And of course, in this range, that is cut-in wind speed to rated wind speed, the power output is increasing because input power is increasing. But why is it not increasing in the range from the rated wind speed to cutoff wind speed? This is done deliberately because rated wind speed means the wind speed at which the generator capacity is reached, and we cannot overload the generator. So we have to restrict the power output of the generator. That is possible only by restricting the power input to the generator. Means from this wind speed onwards, for the higher wind speed, the turbine will not increase its output even when its power input is increased. Higher wind speed means power input to the turbine is increasing, but it's not allowing to increase the output. How? That means it has to reduce its efficiency. The CP value. This is where I was telling you earlier that here in this case, that is above rated wind speed, it will be brought down. The operating point will be coming down, and the final the final wind speed, the cutoff wind speed, that CP value will be very small, very small. It's very small means coming up to 1 or 2%, and beyond that you cannot control. That's why we make it as a cutoff. So this is the way wind turbine generator is operating. And remember, even though I am also an electrical engineer, I have a lot of respect for this wind turbine because wind turbine is taking all the pressure to keep the power output constant, but by withstanding the power input, whatever it is, isn't it? From here to here. From the rated wind speed up to the cutoff wind speed, the electrical generator is a feeling that there is a constant input power and it is delivering constant output power, very safe. But who is protecting the generator? The wind turbine only. The wind turbine is exposed to that. No, not only that. It is taking all the pain and extracting only that constant power, keeping the generator safe. At cutoff wind speed, we are disconnecting. We are disconnecting means we are stopping the generator. Actually, that process it's a 3-stepped
Sir,
that will not be there. So no power is extracted and it's not facing the wind. And after that, it is put on break and the generator is disconnected from the grid. So for the generator, it is again safe. No power input is to given that, and it's disconnected from the grid also. From both sides, it is safe. But think of the wind turbine again. You are changing the blade pitch angle, but still you are taking it away from the wind direction. Wind direction can change anytime. Even then, the wind turbine is exposed to that wind regime. In the field, it is exposed. It has to face that. The threshold, it has to withstand the high wind speed. So it should be designed for a much higher wind speed. 25 meter per second that is shown here as the cutoff wind speed. It doesn't mean that the wind turbine needs to be designed to this wind speed. It should be able to withstand even 90 meter per second because it has to be there in the field even after the cutoff. Okay, so let me proceed. Maybe a bit more faster I will go. Yeah, so this portion that is regulating the power from the rated wind speed to the cutoff wind speed. This is called a power regulation of the wind turbine. The standard practices are pitch control and stall control, and the mix of these two is called active stall. Pitch control, as I told you, if you turn the blade, rotate the blade means changing the pitch angle, then the wind force on that will change. So the efficiency will change. That way, power extraction can be changed. Stall regulation means it is by design. The blade is designed such that from its root to the tip, the pitch angle will not be the same. There will be twist along the blade, and as a result, now the angle of attack in the language of aerodynamics, the angle of attack means at what angle the wind speed is coming onto the blade cross section. That will be varying, and when the angle of attack exceeds beyond a limit, then again the lift force will come down. Making use of that principle, aerodynamic principle, blades can be designed. There are blades called stall regulated turbines. So automatically, we don't need to do anything. We don't need to change the pitch angle. We don't need to do anything. Automatically, above rated wind speed, the power output will be less, efficiency will be less. In pitch control means you have to change the pitch angle above rated wind speed. That means if it is pitch control means from here to here continuously the pitch control, this has to be done. It's not manually, but then it should be programmed for that. The supervisory control should take care of that. Yeah, and then the power output can be regulated constant like this. If it is a stall regulated, then it will be weighting something like this. Means around that rated value. Exact constant figure may not be. I mean, constant value. It will not be maintaining a constant output, but slight variation will be. It will not be rising much above the rated value. That will be a visible effect difference between the pitch regulation stall. In active stall, it's a combination of both. So if at all you do pitching, less pitching need to be done. That's advanced. Yes, let us now discuss what are the different types of wind turbine generator technologies available in the market or developed for the commercial applications. As I mentioned, this can be classified into two: fixed speed machine and variable speed machine. Fixed speed machine is a squirrel cage induction generator. It can be two types in the sense that with one winding and two winding, these are operated normally. All other machines, the DFIG, PMG, or the plain normal synchronous machine, and there is some induction machine again in a synchronous mode that's called the VSIG. All these are variable speed machines. We'll quickly see the systems. Yeah, this is the squirrel cage induction machine. When it is used, the turbine and the gear, then you have the induction machine that will be connected to the grid through a transformer. Usually all these machines, even in large systems, the electrical generator will not be of 11 kV. That is in conventional power plant, no? So this will be 590, 650, 750 volts, like that only. And squirrel cage machine, the magnetization is from the grid. So that reason, power factor improvement, need a capacitor, a bank, and with change in wind speed, the power will be changing. And easily you can understand from the equivalent circuit that with change in active power, the reactive power also changes. As a result, the capacitor bank has to operate a variable mode. Means the switching of capacitor will be required. So that is another requirement. If ordinary electromechanical switching or electromagnetic switching, if you do, that's not good for the capacitors. So you need to do soft switching. Another speciality of the system that we need to remember is that this machine cannot be started as a generator. The induction machine has two modes of operation. Below the synchronous speed, it's motoring. Above the synchronous speed is generating. So at rest, when you are starting it, even when the wind speed is rising, initially it's a motor. So initially it's a motor means the moment you are connecting to the grid is driving it as a motor. And then on the other side, the turbine is also driving it. With the two torques given, naturally it will accelerate and it will go above the synchronous speed and becomes a generator. But then that acceleration time is significant. During the acceleration time, that's a few seconds, more than a minute it can be sometimes. In that case, the loss of generation means loss of energy will be there. That is, wind speed may be there, but still you are not able to extract it because the machine has to come into generating more. With a 4-pole machine, from rest when it is starting, because initially it was working, then wind failed, wind fell, wind speed came down. Naturally, it will go to motoring mode. We cannot allow the system to work in motoring mode. No, instead of a wind turbine generator, it will be a motor and consuming power from the grid. So there will be sensors after the minimum or the maximum permissible time, like 60 seconds or 90 seconds, it will cut off, it will be idling. Later, when the wind picks up, it will start again as a motor, and it has to accelerate up to 1500 RPM. On crossing that, only the generation happens. So that's where the idea came that how about having two different windings in the stator itself? Either one will be connected. For low power, a 6-pole winding will be connected, so that synchronous speed is 1000. So the acceleration time is less, and it's a low power winding. Losses also will be less. As a result, the cutting wind speed will be less. So overall efficiency will be high. This is a principle, simple working principle of the squirrel cage induction generator based wind turbine. Coming to the DFIG, the DFIG is a slip ring induction machine. Slip ring induction machine means the rotor also has a winding. Other connections are the same. The stator winding is synchronously connected to the grid, but the rotor winding is asynchronously connected. What does it mean? That means there is an AC, DC, AC link. There is one converter, which is effectively for power, it's a rectifier, and then there's a DC link. Then there is a grid tied inverter and the filter, harmonic filter. Again, it is connected to the grid. So it's a synchronous connection of the stator and asynchronous connection of the rotor is there in DFI. The turbine can be stall regulated or pitch controlled. It doesn't matter. Now, rotor power output is a slip times the stator power. Again, all of you being electrical engineers, I believe that you know that here, suppose the power, in the super synchronous mode, it's above synchronous speed, it will be acting as a generator. Then power can flow from the stator to the grid. Say P is the power given, and it's operating at a slip S. In that case, the power given from the rotor side to the grid, this will be slip times P. So that means for the same size of the machine, an extra component benefit is the extra power is the output capacity is more. That itself is an advantage when you are comparing the production, the profitability, the squirrel cage system. So usually these machines of DFIG are designed for 30% slip, up to 30% slip. So 30% extra power is coming. If it's a 1 megawatt machine, 1000 kilowatt will be coming from the stator. 300 kilowatt you can get if it, with a 30% slip from the rotor. So that is the advantage of DFIG, one advantage. And then there is provision for super synchronous generation and also subsynchronous generation also. We'll see that. So it's a variable speed operation. 30% variation means that will be visible. And if it is 30% variation above synchronous speed, that is super synchronous. And then if you consider 20% or 30% slip below synchronous speed, means subsynchronous generation. So 30 plus 30, 60% speed variation. So efficiency, significant change, increase in efficiency, overall efficiency will be visible there. Power factor correction is not required here because you can do that with these converters. The rotor injected voltage, it's a phase angle, effectively that will be related to that. Or if you tune with the controls of one of these converters, the power factor correction can be done. So this is the principle of the induction DFIG, and I will show you. Yeah, we said that the subsynchronous generation and the supersynchronous generation both are possible. Now, what is it? These are the four quadrant operations of the slip ring induction machine, the DFIM, WFID induction machine. It can have either subsynchronous motoring. This is common. We all use the motor subsynchronous. It can have supersynchronous generation. Yes, that is also. All the induction generators are normally supersynchronous generators. In addition to that, there is supersynchronous motoring possible and subsynchronous generation is also possible. So in DFIG today, we make use of the subsynchronous generation in addition to supersynchronous generation. Yeah. This is the advantage. It cannot be done in squirrel cage. So what is it? Supersynchronous generation means from the shaft, through the shaft, that is from the turbine, you are giving the mechanical power, PM, that is a power input. Then from the stator, you are getting a power output, stator power output, PS. From the rotor also, slip times that stator power is coming, PR. So that is why we call it a doubly fed, the two feedings. This happens above synchronous speed, the supersynchronous. Instead, the same, the turbine is giving power input PM and stator is giving a power output of PS. Part of that, if you are feeding back or from other sources possible, if you are giving PR, a rotor power, your power is injected to the rotor. Supersynchronous rotor power is coming out. Instead, you circulate some amount of power. In that case, you can control the speed at which this happens. Below synchronous speed, it's possible generation. Generation means you're getting power from the stator. That's a generation. It's not required that a rotor also gives power for generation. And in supersynchronous generation, you get power output from both. But in subsynchronous generation, this is circulated, small amount of power is circulated to adjust the slip. And that slip can be positive. Positive means that is below the synchronous speed. So that's why we call it a subsynchronous generation. And together, if you operate, as I told you, maximum up to this, it's not happening commercially now, but still it's possible, can be done. Yeah, recently there is a development in DFIG, that is brushless DFIG. Some research work was done 1 or 2 years back at the university itself, where slip ring machine, the major disadvantage of the slip ring machine is that it needs slip ring and brushes. The wind power plant is totally unmanned, fully automated. With a SCADA, it's operating. So fully automated. Not only that, SCADA is that the SCADA has a communication either through GPRS or fiber optic to far away control room, and from there can be started, stopped, everything done. Only for major repair people to come there, otherwise nobody is. In such a case, having a slip ring and brush for frequent, it has periodical maintenance, everything, but still that periodicity increases with the slip ring and brushes. Large machine, megawatt level. To avoid data, researchers have suggested this and even developed data that in the stator itself you can have both the windings. You have the two windings that you can have in the stator itself. So stator winding and rotor winding. The rotor winding can be put in the stator, and the rotor will be it's called a nested loop rotor. That's what you are seeing here. A special squirrel cage rotor. If you keep, then the stator will be having an additional stator winding, two winding. So the induction will be happening onto that as a second winding, and just like all other operations are similar. It will be one will be synchronously connected. The main stator winding will be synchronously connected with the grid. The additional secondary stator winding, that will be asynchronously connected. That will be having that variable voltage and variable frequency, or slip voltage and slip frequency will be there. So otherwise, it performs everything similar, and advantages are there. Not commercialized in large level, but is underdeveloped.
Excuse me, sir.
Yes.
Sir, if rotor winding placed in stator, how does it rotate, sir?
No, it rotates as induction. No, the rotation, that's why it's a squirrel cage rotor is provided. Sorry. You are seeing
Yes.
the rotor winding or rather the rotor bus, closed loop. It's a short-circuited bus. Only issue is that it cannot be just ordinary squirrel cage. In ordinary squirrel cage, the induction is coming from one winding only. So here there is a mix actually. The two windings of the stator will be having different poles also. So that's why a special design is required. So it can rotate. Induction will be handled with that rotor circuit. Okay.
Okay, sir.
Yeah, the next major machine is the synchronous generator. It can be the alternator with winding, the wound rotor synchronous generator, or it can be the permanent magnet generator. Both are used, and as a significantly out of the say 12 manufacturers in India, at least 3 of them are manufacturing permanent magnet generators. But only in India, means in general I said. We had 15 manufacturers, but nowadays only 5 or 6 are there. Yeah. So here the turbine is there and the generator. If it is the conventional traditional alternator, that is wound rotor, then the gear is required. Otherwise, if it is permanent magnet, then gear is not required. Why? The reason is that gear was to keep that difference in speed between the turbine and the generator. Now here, if you can increase the number of poles in the generator, then the speed can be brought down. But then the number of poles required will be very large, isn't it? With the 4 poles, it is 1500, and 40 poles will be required to bring it 10% less actually, and that is 150. Again, 80 poles for 75. If you go on increasing that, maybe 150, 160 poles will be required to bring it down to that 15 to 20 RPM range. But it is possible. How? It is possible with a permanent magnet. With wound rotor, it's not possible, but with a permanent magnet, it is possible. That is why permanent magnet machines have come. So here, as you see, after the generator, the entire power. If it is synchronous machine, means okay, for every power, the speed has to change. The speed is changing means variable voltage, variable frequency operation. So you cannot synchronize with the grid. This machine cannot synchronize with the grid. That's why the AC-DC-AC link is here. There is one rectifier initially, then DC link, then a grid-tied inverter. It's connected to the grid. This is the permanent magnet generator, WT-driven EMG or WT-driven SG. So here, it's interesting to note that it's a synchronous machine. So synchronous machine is asynchronously connected with the grid. Previously, the asynchronous machine, that's induction machine, that was connected synchronously with the grid. So that is the grammar here for the wind farms. So synchronous machines will be asynchronously connected and asynchronous machine will be synchronously connected. Anyway, if you use a multi-pole permanent magnet generator, then the gear can be avoided. So to reduce the gear and the gear losses, this technology came in, the efficiency further improves. Moreover, the variability in the speed, that is that lambda omega by b this can be made more proportional. The way the rate at which v is changing, omega also can be made to do that, and in that case the efficiency will be significant increase in efficiency. DFIG cannot go to that extent. Beyond that it can go. For all these reasons, this machine is liked, preferred by users. One interesting thing is that I'm showing a figure. This photograph is of the Enercon machine. It's a PMG type. It's a E40, 300 kilowatt machine. You know, that ring you are seeing here, that is its generator. We call it a ring generator because its length of the generator is only 30 centimeters. Is this? Whereas the diameter is 2 meters. To accommodate all the poles, you need a larger diameter. But then D square L, that is the volume or the capacity of the machine. With increase in D, naturally L will come down. Excuse me. So the main advantage is increase in efficiency. Additional advantage is that your nasal size is reduced. You have a simpler system. It can the operation all will be convenient. Of course, there should be some inertia on the tower top. If very low inertia, that's also a problem. But anyway, Gear is not there directly. You can couple it. Simplicity. A few the number of parameters in SCADA can be reduced when the gear is not there. Gear is problematic. In a SCADA, mostly they get the alarm for the gear oil. Gear oil is there. That is for the lubrications. Temperature needs to be monitored, and if it goes up with the alarm, they have to switch off. Remotely, they do that. So, variable voltage, variable frequency operation, and because of variable speed operation, efficiency is high. And since you have an inverter, retired inverter, it can be controlled for any desired power factor. So importing or exporting power is possible here. Yeah, this is VSIG, variable speed induction generator, wind turbine. Its development, the history is interesting. It was in 1931, I believe, 1924 or 1931 practically. The first induction generator with a turbine was developed and tested by Russia. It's a 100 kilo huge machine. Before that, mostly synchronous machines were used. Now, since then, and then in 1980s, in 81, in California, when they went for the field installation of these machines, that became the model. Up to 2000, for 25 years, induction generator ruled, induction machine ruled. And you know that as the motor applications, induction motor is ruling all over the world, and it will continue its rule. And for that reason, everywhere people are so familiar with its construction, operation, maintenance. That's why the cost is less. But still, after this, replacing induction machine when synchronous machine was brought, the people are wondering, electrical engineers were wondering, oh, at least some things it's unfit power generation. Conventional power generation also we are not using. But then the question came that the synchronous generator you are using, not in synchronous mode. In conventional power plant, you are using a synchronous generation synchronously connected. But when it is to be used, you see here it is asynchronously connected. The entire power is passed, is rectified, and then AC. If that is the case, this is possible. You want a variable speed operation, and that is made to happen by the variable voltage, variable frequency operation. That is possible with induction machine also in a similar way. You look here, the turbine, only that gear is required. Then this AC, DC, AC interface, asynchronous interface is possible with induction machine also. So this concept came and it was commercialized also. We had one or two manufacturers, even there are machines installed, Tamil Nadu, this type of machine. But later that company became bankrupt and discontinued. A lot of research happened and unfortunately industry didn't adopt it. So in the market today, VSIG is not there, but otherwise it gave a challenge. Gear is added, but the cost of machine generator is much reduced. The cost of a permanent mag generator is very huge. Yes? Any question?
No, sir. No, sir. No, sir.
Cost of permanent magnet generator is very big. If I make a comparison, at present anywhere, squirrel cage machines are not there in the market. When squirrel cage machine was there in the market for a 250 kilowatt generator, wind turbine generator, the fixed speed machine was costing something like 90 lakhs, 250 kilowatt machine, 90 lakhs for the squirrel cage with the squirrel cage generator. At that time, this machine, permanent magnet machine was introduced with 135 lakhs. So 50 lakhs difference was there. Almost 50% cost difference was there. But still, some people agreed. Or initially, the manufacturer itself developed a wind farm and demonstrated it. Seeing the performance, people started buying it. Later, squirrel cage machine is discarded. Nobody is manufacturing because there is no demand for that. But permanent magnet generators are more and more used. That large large hike in efficiency is possible because if you are using permanent magnet generator, efficiency is very high. That's why you are using. But otherwise, the cost of the machine is very high. And I should also mention, even though the time is less, that using permanent magnet in electrical machine is not a good practice in a larger perspective. It started with the wind, and otherwise in very small machines only it was in use. Later, now in electric vehicles, the large vehicles are all preferring, all even four-wheelers are preferring, the manufacturers are going for permanent magnet. They have the option of induction motor, but still they are going for permanent magnet. Why I'm saying that it's not a good practice? These are rare earth magnets. It's mining. It's happening. It's not happening in India. Happening in China. From China only, all these magnets are coming, and also in some African countries and in US. Also, it was wherever the mining is done, quite a lot of environmental issues they had. People could not stay around. These all those issues were so. Environmentalists, they are against mining of rare earth for making permanent magnet. So that should be limited. We should not use it in each and every case, only when it is essential. Solutions, EV solutions can be made with an induction motor. Anyway, in wind, of course, it helped. And in the beginning, in 98, when it came, people were skeptical because prior to that, permanent magnet means it had a life of 4 to 5 years. After that, we had to remagnetize it. But they said these rare earth magnets, we don't need to remagnetize. Its life is 25 years. The machine installed in 2000 is yet to complete 25 years. But after 20 years, it's still strong. There is not much weakening in the magnet. So they are powerful. They are powerful, but the other issue is them. Yeah. So this is VSIG. But in the field today, people do consider that they have only two options, DFIG and PMG. SCIG is not there for very small applications, 100 kilowatt at ranges, such applications. There is one manufacturer in Tamil Nadu. He's still making it. One or two machines will be sold for those who want to continue with that. It's for replacement and all. Otherwise, it is DFIG and PMG. This is the story with the large wind turbine generators grid connected. I said in the beginning, cannot be considered for microgrids. But otherwise, this is the existing technology. Now, even the slip ring induction machine doesn't need to be used as a DFIG. It is used, this tried and developed by the Suzlon in one of their models. On the rotor, you can have an external resistor and you can use it to vary the slip. Sometimes when sudden power surges are there, that at that time for control, this is helpful. This is found to be helpful. Then, yeah. So let us come to the major part. Almost more than an hour I spent the background. Now let us think of microgrids. That is the topic of the workshop. What I say is this: microgrids will demand standalone wind turbine generator of smaller size. Microgrids will be operating in grid-tied mode and also in standalone mode. That will be required. There can be autonomous microgrid that will not be planning grid connection at all. But other microgrids will be having the option of islanded operation. In that case, the wind turbine generators that should be able to operate standalone. So all the machines which we discussed so far is not for standalone operation, it's all grid-tied operation. And microgrid, being micro, the size required is smaller. The largest wind turbine generator in use today in offshore is 12 megawatt single machine. Onshore or on land, that is a better usage. On land, these days they are installing 2 plus, above 2 megawatt, 2 to 3 megawatt. These are the machines installed. But then we may consider medium-sized machines in kilowatt range for future microgrid operations. And when you think of smaller machines, there are certain subsystems of the large wind turbine generator which are not cost-effective in the small size versions. No, several components are there. It is having the 2-3 components or 2-3 subsystems I will explain. In large systems, okay. At the large systems, its cost is almost 6.5 to 7 megawatt. Sorry, crores per megawatt. Say 7 crores per megawatt. That's a cost. Now, if you translate that to smaller machines, that will be coming much more than 10 to 12 crores per megawatt. Not megawatt level machines, but per megawatt. For comparison, I compared with megawatt value. Smaller machines will be costing more because certain components we cannot have a proportional cost reduction. One such system is this yaw mechanism. You know, the yaw operation. That is on top of the tower, the nacelle, that housing on the top of the tower that has to horizontally move, rotate, not continuous rotation, to adjust to the wind. It has to face the wind always. That is the yaw operation. For that, there is yaw motor inside and the gears. What the photograph is, when you know the tower and the top of that in nacelle is. The tower has a bottom door. If you enter the tower through that door and look up, then this will be what you will see. There is the yaw motor and all these gears, so that spring bearing on top of the tower that will be rotating along with the nacelle. This cannot be, it is not that easy to have a miniature of this in small machines. It will be very costly if you do that. Another thing is regarding the braking. Initially, I told you that I will tell you the braking is an interesting thing. Wind turbine braking is not an easy thing. Of course, there is a hydraulic brake, mechanical brake available in the system. So the brake pad and on the brake drum, this will be working on the brake pads. You can see the two brake pads. But you cannot apply the brake when the system is working. Consider a single machine, 2 megawatt machine. There, if you suddenly apply the brake pad, then it will not be braking. The pads will get damaged. It's not an easy task. So the brake, you can apply the brake when the system is not rotating. And you will ask, okay, then what is the use of the brake? When I say that your vehicle, you can put the brake when you after the vehicle has stopped. Well, there is a difference. So here, the purpose of the brake is not to stop when it is working at such a high torque with a large amount of power. People used to wonder, looking at the machine which I have told you initially, that's installed here in Palakkad, in Ahalya, and I had the fortune to be the project leader of that. So its RPM was around 10 to 12 RPM. So looking at it, people used to wonder that such small rotation, can it bring 2000 kilowatt? Yeah, but it is. Yeah. So the purpose of the brake is, once if you're stopping it, then you apply the brake so that it will not turn further. So arresting the shaft, the rotor, that is the purpose. So how to stop it? You have to start with the aerodynamic braking. That's a pitch control. Initially, we have to turn the pitch. You know that the small pitch angle will help you get a large lift force and rotation. If the pitch angle is 90 degrees, then there will be hardly any lift force, only drag force will be. So if you change the pitch angle, it takes time from bringing it from 5 degrees to 90 degrees, it takes time. So, but you do that slowly. Suddenly you cannot change it. The stress on the blade will increase. Stress on the blade at the root to the tip will be different. So there can be shearing force. So many issues are there. So pitching has to be done, and the yaw control, as I told you, the yaw operation I told you. Turn it away from the wind, so it will stop very slowly. It will be moving. At that time, apply the brake. Now, in a small machine, if you incorporate all these things, there are Chinese machines available. 5 kilowatt, 10 kilowatt machines are available with all these facilities. But to my understanding, only 1 or 2 people in India who purchased it, I could interact. They were not very happy with the operations of this, the life of this subcompanies. Then, yeah, this is the pitch control, the issue. This is the way they do. This is the hub. On the hub, you are fixing if it's a 3-bladed machine, the nacelle will be having a hub and the 3 blades. You can see the 3 openings, one on top, the other on the side, and this opening. So the 3 blades will be fit there. You see the ring here. So this will be rotated. There will be earlier hydraulic mechanism was there. Now a variable speed drive can be used. And very slowly they are operating it so that the stresses are not there. There is a scope for some more work here. If you're using a VSD and if it is taking a feedback on the stress sensors planted along the blade, root to tip, that will give an idea about the strain. And with that, you can decide at what speed the pitch control, how fast the pitch control can be done. Well, that is not a topic for today, but anyway, let's come to the standalone machine. The standalone machines and smaller machines, mostly permanent magnet generators. So it should be, if you are using a permanent magnet generator with the wind turbine, you should have the wind turbine and directly you can couple it. Because small turbine, you can allow it to run at 1000 RPM. That's not an issue. So the permanent magnet generator, small machines, are not having 100 poles or 1050 poles. We'll be having some 18 poles or say 12 poles like that. Less number of poles will be there. So the size of the machine, just like a ceiling fan, it is made. The ceiling fan itself is having 18 poles. It's not permanent magnet, but another way. And then it needs that AC/DC AC interface that's rectify the power, because change in, as I told you initially when we were discussing, for every wind speed, for the power flow equilibrium, power transfer balance, for balance, different speed, shaft speed is required. For every wind speed, a different shaft speed. A different shaft speed means a different voltage and different frequency. So it has to be a variable voltage, variable frequency operation. So you need to rectify it and then have an inverter. So this inverter has to be a grid forming inverter. Inverters are grid tied inverter and grid forming inverter. Grid forming inverter means it decides the voltage and frequency are fixed. It will be generating that voltage and that frequency and maintain it. And then it can be connected to a load. This is a simple idea, the simple concept, but will the load have a variable power consumption profile in synchronism with the generation? It's a question to be asked here. Wind speed will be varying, so the power output will be varying. The power given to the load also will be varying. Is there any load that can take a variable amount of power? If you have a lamp, it has a fixed watts, so demand is fixed. Even most of the appliances, equipment, demand is fixed. There is exception. Say, suppose for space heating or water heating, you can have a resistance type of heater, and a resistor can take a variable voltage. So power also will be varying accordingly. Such applications are there, but otherwise, here there is an issue that the load terminal voltage will not be maintained constant if you do this way. So there is a need for electronic load controller for the voltage regulation, or there is a need for voltage regulation. What is done for that? Now, for that, the turbine, the generator, and the rectifier. After the rectifier, in parallel, you arrange a dummy load. You have your regular load, and then in parallel, you can have a battery. The battery charge, discharge control you can do. So, to keep the voltage constant, what is required? Power balancing is required. Many students overlook this actually. They think that you can control the voltage irrespective of the power balance. Here, the power generated from here and the power consumed, these two should be the same. If there is any variation, if there is more generation coming, the system will force the load to consume that entire power. For that, if it's a resistive load, the terminal voltage should change. So if you want to keep the voltage constant, the voltage regulation means now whatever generator power is coming, you allow the load to consume its share, and the excess power you divert to a dummy load, or you can divert to battery charging. Once the battery is full, then you need a dummy load. Similarly, when power generation is less, when speed is less, the load demand is not met, or in other words, the terminal voltage is going less. For voltage regulation, you have to discharge the battery. If that is not possible, or if dummy load is connected, you can remove it. Completely removed, still voltage is going down, you can discharge the battery. Still voltage is going down means you have to shut down the plant. That's not the So voltage regulation is a requirement here, and the electronic load controller, that is practice was developed much earlier for micro hydel systems. That is through a chopper, a dummy load, a resistive dummy load will be operated, and this will sense. This chopper will have the controller means it will sense the voltage across the load, the voltage. Any change in that voltage, that duty ratio will be adjusted so that the change is abated, that error is killed. That is the operation here. The small or standalone generators with a fixed load, dedicated load, they operate like this. So there is a wind speed range below which it cannot operate. Can operate if battery is there, and if you make the battery pack thicker and thicker, larger and larger, the cost is increasing. In fact, small wind turbine is not commercially matured or not commercially successful. It's not popular because of this cost issue. Cost issue and operational issue are also the operational issue in the sense that I told you, dummy load is okay. Otherwise, with the battery load, if you're doing, then after the battery is full, it will accelerate. suppose semi-load is not there. You are trying to manage with a battery alone. This is not there. In that case, once battery is fully charged, further um, any generation above the load demand, um, uh, that will be a problem. The load may get damaged. If it is battery alone, it cannot absorb. So power is taken from the wind, and generator is not able to transfer it to any load. There is no sink. And the only possibility is that the turbine will accelerate kinetic energy. That's the only way it can store it if it is not delivered. So it will do that, but how long? Till the first blade flies away. After that, it will not work. This happens, and this has happened several times, and that's why I usually relate to that incident in Coimbatore in 2005. Around 2005 to 2007, there were 7 manufacturers of small. Today, there is only one, and that too is not very regular. It's because of such operational issues. Yeah. Instead of having an electronic load controller in a single in each machine, we can think of the microgrid. If it's in part of a microgrid, I'm showing a microgrid here that has a few grid buses. 4 or 5 buses are there. In one bus, the wind turbine power plant is there. There is solar plant in another. Here, you can have a battery storage with a charge and discharge control. So that will help for this. It is faster, but it is size is smaller. And along with that, if you have a pumped hydro, it is still better. Pumped hydro means here, usually in a pumped hydro, the turbine generator will act as the pump one. That's not the case here. You should have a separate pump hydro. The motor pump will be there separately, different from a turbine. Micro hydro is that is the turbine generator, and the hydro storage is that's a motor pump. And there should be variable speed drive. Seeing what is the frequency change here, or power balancing here. If it's an AC system, sensing the frequency, you can do that. So that is stored charge or discharge. For pump hydro, you can only charge it. You cannot discharge it. That discharge is from the micro hydro. And battery, the charge discharge control can be done that way. Instead of having a single, each machine, in that case, each machine doesn't have an ELC. Instead, for all the machines together. In fact, this storage, it will work for the solar and wind together in a hybrid microgrid. Energy storage management. We call it a dynamic energy management system. Can help for balancing. And you need this microgrid to be smart. Then only all these activities will be done. On every bus, there has to be that is RT, the remote terminal data collection unit. So this RTDCU, like you can call it a distribution PMU. That way, in that speed or that rate, should be sampling the parameters, that is the voltage or current or frequency, and with that, this management can be done. That's all. That is a smart microgrid. So dynamic energy management in smart microgrid. Why is it smart? Means this communication, this data communication, data sharing, and the management system that will be required. TEMS is dynamic energy management system. This will be required for the power balancing on the microgrid. So we call it a smart microgrid. There can be smart microgrids. Several smart microgrids can be interfaced to grid. See, here, this is one microgrid is shown in detail here, that has solar, wind, even gas turbines, micro turbines, battery storage, and different types of load, commercial, industrial, and residential. And it has 2 modes of operation. This is a hybrid in a source. Is hybrid in mode of operation, either grid connected or islanding. If it is islanding, means it will be controlled by the EMF separately. Otherwise, each unit, you see the solar to DC-DC converter and retired inverter. Then wind is also rectifier and inverter. Turbine, micro turbine also rectifier and inverter. That way, this is connected. In islanding mode, one of the 3 inverters will be acting, will go into grid forming mode, hybrid, and then others will follow suit, synchronize with that. So several such microgrids can be connected to the grid. That is one futuristic idea. There, wind turbine generator has a role, or even it can be a DC microgrid. A DC microgrid also will be having multiple sources, means a hybrid sources, solar, wind, hydro, with battery storage, as explained. A similar can be grid connected or islanded. That is possible. Here also wind is possible. See the small wind turbine that is having a rectifier first, and then it and a hybrid microgrid. So for hybrid distributed generation on hybrid microgrid means network. Hybrid needs to be defined in three ways now. Initially, by hybrid we meant only different sources, wind, solar, hybrid. A conventional and a non-conventional source. That's the way hybrid was originally defined. Later, different sources, integration of different sources. That's why we meant by hybrid. Today, hybrid means it can be hybrid of sources. Secondly, it can be hybrid of modes of operation, grid connected and islanding. So if it can, the transition from one mode to the other mode automatically as per requirement through the controls management system. If that is possible, that is called a hybrid microgrid, again, hybrid operation. And thirdly, if you have a DC network and AC network, see in this case there's an AC grid and a DC grid. These are interconnected with a bidirectional converter, so that exchange of power will be happening. And you can have PV on the DC side, battery also on the DC side. But it's better, it's ideal to have the wind and the hydro on the AC side. Now, these two can be connected, means wind finds application in microgrids, even in the hybrid microgrids. Fine. Yeah, when it comes to standalone wind turbine generator, I said initially that largely people are using permanent magnet generator. And the recent research, if you look at, DFIG is preferable, right? DFIG is preferable to PMSG in medium-sized wind turbine generator. Why? Owing to lower cost and its unique capability of maintaining stator voltage and frequency at desired levels, besides managing energy storage all with a single unit. You can have DFIG in a standalone microgrid or a standalone unit. Here actually load, AC load are there, and the rotor, there is a converter here, and there is a DC link with battery. With this arrangement, we can produce, that is, we can regulate the voltage and frequency on this AC grid. This is the AC grid. If required, this is also bidirectional. This converter also should be bidirectional. In that case, the power excess and deficit in both directions, it can be arranged. Here, similarly, the DFIG can operate in supersynchronous or subsynchronous mode. That is, the power either will be injected into rotor or will be taken from the rotor, and that extra power can be stored in the battery. Deficit power can be taken from the battery. If it, cost will be much less. So that's what it's saying, that it's managing energy storage in a system, in a microgrid. You need energy storage. That energy storage can be utilized here. And then it can, no extra things. All other components. This is regularly used for storage. DFIG is coming there, and only these two converters, both are bidirectional, are required for its operation standalone. So standalone operation of DFIG is possible. It's been proven by researchers, and will be getting commercialized. So then here, stator maintains nominal frequency and voltage as controlled by the rotor side bidirectional converter. This will be the control. The rotor voltage, the magnitude of the rotor voltage, and its frequency. This is to be decided in such a way that at a what slip it should operate, whether above synchronous speed or below synchronous speed, all can be decided, and you can regulate. The stator voltage will be fixed nominal voltage and fixed nominal frequency. Supersynchronous or subsynchronous generation is possible. Changing the rotor frequency injection forces change in omega and in turn change in CP. it gives a possibility for generation control. In the for voltage regulation, you have to change the rotor frequency. That is what is done here. Now, beyond that, okay, if that is maintained, after maintaining the voltage regulation, you can also consider that by changing the rotor frequency, effectively you are changing the angular speed here. That means the CP of the turbine is varying. So for a given wind speed, you can change this, its CP, its efficiency. What does it mean? It is generation control. Usually we believe that from wind turbine generator, we cannot control the generation. It's possible in a limited extent. Maximum power point can be extracted off MPP, away from the maximum point. When there is no demand and the system and storage is also full, you cannot produce maximum. All these are possible with a system, standalone DFIG. Yeah, this is simply and quickly explaining the principle of that. This is a steady state equivalent circuit of a standalone DFIG you are seeing. You are familiar with that. And this is the load, being a generator on the terminal, there's a load. And on the rotor side, that's the comes from that. So here you'll get this equation. It's not very difficult from the equations to get this relation. The stator voltage can be expressed as a function of the slip, that is rotor speed, then a rotor injected voltage VR, and the load. Now, if any of these three varies, then stator voltage will be. So what you have to do? VS should not vary, it should be kept. So variation in either the wind speed or the load will cause a change in rotor speed, which in turn will cause variation in VS. This is usually happening. Even if you adjust VS at such value, a change in load will cause change in VS, means a stator voltage, or a change in wind speed will cause a change in that in standalone. So yet VS can be kept constant if the rotor voltage, rotor injected voltage, that is VR, is such varied as to counteract the effect of rotor speed change. If the rotor speed will change, and at that time, if your injection, rotor voltage injection, VR, if you are adjusting such that the change is nullified, so voltage regulation is happening. Similarly, this omega relations, angular speed relations, you know that mechanical and the electrical omega. So here also there is possible, that is, you can identify a rotor omega frequency that is required to obtain the stator frequency. So this method is recently published. We call it dynamic frequency tracking because it's much simpler than the methods previously suggested. It has two loops, control loops. One is a feed forward loop that compares the omega and fix the reference frequency, omega, rotor frequency reference. Similarly, the other one, as usual, it's a feedback loop. It's tracking the stator voltage, and the rotor voltage magnitude is first calculated from the V by F ratio. You have to maintain flux constant. So you have a V by F. Stator frequency, the V value can be first calculated, and then use a PI compensator, PI controller. And from that, you can obtain the rotor VR reference, that is, what is the rotor voltage to be injected. Accordingly, the PM can be, PW can be decided. So the corrective action against any disturbance triggered by the load or wind speed change is taken jointly by the two controllers, the speed and voltage. That is called the dynamic frequency tracker. Simple. You need less sensors and less controllers. Yeah. So in this standalone operation, when it is operates in a microgrid, the DFIG, the two-quadrant operation, that is subsynchronous generation and supersynchronous. So for subsynchronous generation, you know, turbine will be giving the mechanical power input and the stator will be giving an output. To the rotor, there is an injected power. So this is, that means when mechanical power supplied to the machine is less than the stator power required. The stator, there's a load. So it's less than the load demand on the stator. In that case, you can use it, the subsynchronous operation. And here, even MPPT, maximum power point tracking, that means lambda at its optimum value, the design value, that can be kept CP max, max efficiency of the turbine, because the generation is less here. In that case, from the storage, you are taking power. So that can be the maximum power tracking of turbine should be done. When we say this MPPT, maximum power point tracking, this is different from the MPPT in solar. In solar, the MPPT means that it's a static system. That's a PV cell, basically the PV cell or the PV module. The photovoltaic module is made to operate at the point where, for a given radiance, the operating point is giving the maximum power out. Depending on the load impedance, the operating point will be varying. That is, the power output of a solar panel will be varying even when the radiance is kept constant, depending on the load impedance. So that load impedance is you cannot change. So they're having a converter in between and adjusting its ratio, duty ratio. You are managing such that adjusting the voltage to that load, you can keep the panel operating at its maximum power points. But then maximum power point tracking in WTG is altogether different. On the generator, there is nothing done. It's on the turbine. Earlier we said the CP max, the power coefficient maximum value. Where did it happen? At optimum lambda. There is a design lambda. So making the turbine operate at its maximum power coefficient. That's called maximum power point tracking here. Yeah, supersynchronous operation. Supersynchronous operation means mechanical turbine power input, stator power output, rotor power output. So this is possible when its turbine is producing a power that is greater than the demand on the stator side. On the AC network, if it's in a hybrid network, AC-DC network, on the AC network, whatever load is the, say that is PS, stator power requirement. The PM, mechanical power, turbine power, if it is more than that, then from the rotor also the power slip times stator power will be delivered from the rotor that can be stored in the battery. Or on the DC grid, it has AC grid and AC network and DC network. On the DC network, there is some demand which is unmet. You can give it the. Here also MPPT can be practiced, but not in the full this thing. The range will be then the autonomous hybrid microgrid. Suppose we are making a microgrid that is autonomous. This will be a futuristic requirement. Grid connected, that is one mode of operation. Islanded, that's other mode of operation. So for the islanded operation, that's where the control is, coordinated control is required. So just quickly see what are the controls required. If you have a hybrid microgrid, means it has an AC network like this and a DC network like this. On the AC, you have the DFIG, as I explained earlier. These two bidirectional converters are there, and AC load is there. On the DC, you have the solar generation, and we have a converter. This converter is for its MPPT, maximum power point tracking, and you have a battery energy storage. That a bidirectional converter is required for charging and discharging. Then you need a deferable load. There's a DC load. In addition to that, a deferable load. Deferable load means it can be EV, electric vehicle, or some pumps, because pumps need not be working all through the day. One time in a day you can fill the tank. So when there is excess power available, you can use it. That's why we call it a deferable load. If such a microgrid for a particular place, if it is made, why AC and DC? You know, there's most of the appliances are made DC these days. There is advantage in that. And then when there is a DC generation, better to have those appliances. You can have two different sections, AC section, DC section, in our buildings, commercial or residential buildings. So the two networks will be operated. Means one consumer itself will be partly here and partly here. All these are possible. So that is why such a concept is coming. And here, simultaneously applied multiple controls of it. 6 different controls. One is the AC voltage regulation and frequency regulation. Similarly, DC bus voltage regulation is required. PV generation can be controlled. It's a static. It's a wind generation control is not that easy, but PV generation, photovoltaic generation can be controlled. From the no load to full load. Full load means maximum power. At any point, it can be off. You only need a converter to adjust for that. Instead of MPPT and off MPPT, control also will be required. Or together, you can call it a OPPT, optimum power point tracking. That is what is required in a PV. Then the limited wind turbine generation control means when possible, maximum power point tracking can be applied. Otherwise, operate it away from the maximum power point. And then, yeah, this is another control required. You have this AC network and a DC network. Sometimes AC power generation is high, but demand is less. Then you take it to the DC network. Sorry, this way. That is, yeah, you take it to the DC network, means to the battery. You you can, excess power can be given to the battery, or it can be used for the DC load. Sometimes there is excess power generation on the DC side. DC power generation is available power is high, but demand is less. Then that excess power can be stored, but also it can be given to the AC network and can be used here. This power transfer that can be done through this bidirectional AC-DC from AC network. Any power demand unmet on the AC side. Okay, from the DC side, this converter can take it to the AC side. Similarly, an excess power from here that can be. So this also means be controlled for the power transfer. Yeah. So these are it's one by one. For the AC bus voltage and frequency regulation, these are the converters used for that. Already discussed it. That's a dynamic AC tracking. And then for the DC voltage regulation, this is to be done entirely by the bidirectional DC-DC converter on the battery. Its purpose is that power balancing. Charge discharging of the storage means power balancing. That is the only way to regulate the DC voltage. Like frequency in AC side, AC side is the voltage. So sometimes students misunderstand that the regulation is one purpose, so one converter for that, and then charge discharge, storage is another purpose. No, all these are the same. Why do we store energy? The storage management, that is for power balancing only, the deficit or excess. And when is the voltage varying? Again, the system its own effort to balance the power, the conservation of power. That's why the voltage is changing. So charge discharging of the battery or power balancing or voltage regulation, all these three are the same activity that's done here. Next, yeah, the PV generation control. This converter, it's a AC-DC converter. That is that, as I told you, the optimal power point tracking of the PV. And wind turbine generation control. Here, actually, as I told you, it can be pushed into super synchronous mode or into subsynchronous mode. That depends on the availability of power, means wind speed. Usually for lower wind speed, it will be in subsynchronous, and higher wind speed, it will be super synchronous. And then in addition to that, that MPPT, maximum power point tracking, also can be done. Methods have been developed for that. And also sensing the overall balancing in the system, it can come out of MPPT. So then AC-DC power transfer, as I told you, excess power in any network can be shared with the other network by operating this bidirectional AC-DC converter. Deferable load, yeah. When the battery is full and still your EV is generating or more power it can generate, at that time deferable loads can be operated. You can charge the electric vehicles, or you can pump water pumping systems. Okay. I've not completed, but I think it is better we stop it here and go for a discussion. Vivek?
Sure, sir. Sure. Sure, sir.
Yeah.
Yeah.
So let us look at the chat box. What are the questions which are come, or even people can ask?
Sir, can I read out?
Yeah, please.
Yeah. What are the challenges faced during the grid integration? What are its solutions?
What are the challenges faced in grid integration, and what are the solutions? This, I think, the question is referring to grid-tied systems, not standalone, isn't it?
Yes, sir.
It's a grid integration, yeah. Grid integration, some new challenges are coming. So all challenges are overcome. Let me tell you the previous challenges. That is, you have to synchronize. There are two requirements on the grid when you are connecting any renewable energy system to the grid. One is the synchronization. How to synchronize the inverters? You know that most of the renewable energy systems, like PV inverter, is essential, and for wind turbine generator, again, if it is variable speed type, inverter is essential. So power converters are ruling. Inverter dominated microgrids, IDM, that is the future. Anyway, for the grid connection, you need inverter. These inverters need the synchronization first. So PLL is traditionally used for that, but there are some future challenges for PLL that I will discuss separately. And otherwise, presently the solution is PLL for synchronization. Then active power control and reactive power control. So active power control, this can be for inverter. If you change the reference, so power reference, that control can be done. That's not the issue. But for active power control, it is possible with the photovoltaics, because photovoltaic is a static system, and the power level or its operating voltage and current, that can vary. The power level can vary from the minimum to maximum anytime. And it's very fast also, very quick also. Conventional power plants, compared to conventional power plants, this is the fastest, a very quick variation. Active power control is possible with the PV. When it comes to wind turbine system, the active power control is limited. What you can do that, incorporating some converters. See, you have a DC link there, isn't it? A PMG or PMG means the entire power from the generator is passing through AC, DC, AC to converters with a DC link. In that DC link, if you add a DC converter, a chopper, that variation in the voltage, that will affect the system will go for a different speed. If you disturb the voltage, it will go for a different shaft speed for the same wind speed. A different shaft speed means it will change the lambda, it will change the CP, and the power will vary. So that is the possibility of generation control or power control, active power control with the wind turbine. Reactive power control, when it comes to reactive power control, it is all with the inverters only. The system, so source has nothing to, renewable energy has nothing to do with that. For reactive power control, I had that slide in this, but there is no time. For what we need to do to see is that if you want to operate at a reactive, for reactive power control by the system, by the grid-tied inverter, then the inverter capacity should be in excess of the power rating. What I mean to say that, suppose the wind turbine generator is 1 megawatt. So the inverter is also 1 MVA, or a PV of 1 megawatt, inverter is 1 MVA. There will not be much variation possible in the reactive control. But if the inverter is oversized, some 25% extra, 1.25 MVA inverter if you are keeping, there reactive power, it can be operated at a leading or lagging power factor. So these are the solutions currently available. Such inverters are now, ABB has now given this in the market, where reactive power correction is possible and active power control is possible with the PV. With the wind, this generation control is commercially not done. It's all in the research stage. With the PV, it is already come, not very popular, but it has come. It has reached the market. A few, 1 or 2 manufacturers are there. So these are the major challenges. These were the major challenges. In future, the problem is that, this inverter domination or the population of inverter, penetration of inverters is increasing. And you know that every inverter may cause harmonics issues. Inverter, basically what is it doing? It is switching. DC, by switching, it is producing AC, stepped voltage. And then through filter only the harmonics are removed. But all the harmonics will not be removed. Regulations say that a 5% voltage harmonics are permissible. Okay. So that means with the many inverters connected, there can be considerable amount of harmonics in that. So PLL may fail. The PLL has to get to the phase angle, exactly the phase value of a voltage signal. What is its phase angle that has to be obtained? It may phase, there can be, because of the harmonics present, extracting the fundamental will be difficult. So maybe signal processing tools will be required in future to help synchronization, to extract the fundamental frequency and all these things. And that's in synchronization. Then in active power control and reactive power control, as I said, today the penetration, renewable energy penetration being very low. much of active power control is not done. But in future, we will have to do considerably the active power control, as we explained. This has been demonstrated. NREL, together with IEEE, they conducted a very elaborate experiment, a field experiment in Hawaii in 2018. These reports are available. A number of articles are published in Power and Energy magazine. You can read that. It shows how PV plant, the droop control of a PV plant. It's all published the last 2 years. So active power control, that is coming, and then reactive power control. So in reactive power control, that concept has to come. Today it is not there. For example, today the interesting thing, if you are installing a 1 megawatt solar power plant, and your consultant will say that the requirement of inverter capacity will be less than 1 megawatt, 1 MVA. Why? Because 1 megawatt peak capacity, that is, they call it a DC power, means at standard test conditions, that is 1,000 watts per meter square radiance and 25 degrees Celsius cell temperature, it will produce 1 megawatt. Naturally, to get 1,000 watts per meter square, it has to be noontime, and at noontime, the cell temperature will not be 25 degrees. It can be more than 50 degrees, double. And then the deterioration of power will be. So at rated capacity, it will never operate at rated capacity. A 1 megawatt power plant, a solar power plant will never operate at a 1 megawatt capacity, will never deliver 1 megawatt power. So the inverter requirement can be less than that. A 15% reduction is possible in the size. This is the way the present consideration is going. But in future, if the plant has to deliver reactive power, then it will be the other way. Instead of 1 MVA, you should have a 1.25 MVA. That this will be the solutions, probable solutions. See, there is no point in telling. I cannot dictate the solutions, and I'm not competent and capable also. But these are probable solutions.
Thank you, sir. Sir, the second question is it practically possible to use excess power from wind generation for pumped storage? Is geographical location a constraint?
Of course. Pump storage means if only geographically it suits. See, you need a head. For pumping, you need a head. Before that, you need water. If you have water in plains, it will not help. There has to be a head. So pump storage, why we suggest pump storage? If geographically it is possible, do that, because its cost is less and its energy density is high. With battery, the problem is that to handle the entire excess or deficit energy requirement, a large amount of bulk storage is required, and it's costly. To that cost, this pump storage cost will be less. At the same time, don't think that you can avoid battery, because fast battery is a fast acting. Pump storage will be slow. At millisecond level, it will not respond. The load following requires millisecond level operation, that only the battery or supercapacitor can do that. So a combination of two storages, one long-term storage and one short-term storage, that is ideal. So for the short-term storage, it is the battery or supercapacitor, and long-term storage, it can be pumped hydro if it is available. It should be a separate unit, not the same microhydro. Wherever microhydro is there, wherever hydel is there you can have a pump storage, separate unit, separate equipment. Otherwise, there are other systems also, like there's a thermal storage and large storage systems that also can be used. You can produce a hydrogen. So many ways, many other energy storage systems are there. Those things, whichever is available, everything is site specific. These two I suggested, battery I suggested, because battery and supercapacitor, there's no other comparison for that. Pumped hydro, that is the cheapest. That's why I took it as an example.
Okay, sir. Sir, I am summarizing from 2 to 3 questions. They are interrelated. Basically, they are asking which type of converter can be used for hybrid microgrid configuration, and can interlinking converter be used, and what must be the rating?
So rating depends on the capacity. Now, what is the load demand? What is the generation size? You have to do this design of the system. Requires a simulation study initially. It's a better practice, as one of my scholars has just completed it. Initially, you go for a Homer design. Homer is available, and you can have a Homer design to decide what is the generator capacity matching your demand. After that, you run the system, you run a simulation, and you find what is the excess with the profiles, the load profiles and generation profiles. What is the excess and deficit things which are coming? Um, the power, excess power and the deficit power, not the energy. That will decide the size of the converter, the rating of the converter. And then the type of converter you said, this exchange, if it is hybrid network, then you need a bidirectional converter. That is, it is AC DC converter. It has to be on one side. It is DC network, otherwise it is AC network. That's rectifier and inverter operation, but both controlled operation. It's a traditional conventional converter. There is no change in that. Otherwise, and on the DC side, the converters are DC converters, the choppers which you are using for MPPT and all. Academically, when we teach, we say buck boost chopper is ideal, but not necessary. You can have a boost chopper or a buck chopper. See, it is like this. If you have the DC bus, say 48 volts, and you make the solar array something like for 110 volts, then you don't need a boost chopper. A buck chopper alone will do. Its duty ratio can be varied for the adjustment of MPPT. The other way around, if you keep the PV panel size, its voltage much less than the DC voltage, then only a boost chopper is required. So these are the requirements of the converters, AC side and DC side. The other one on the wind, the converters used means on the rotor side, that's an inverter. See, again, bidirectional. An inverter means it's a converter that can be operated as inverter, AC and DC. So, and you operate either from AC side to DC side or DC side to AC side. Inverter, rectifier operation, controlled converter. All these are conventional.
Okay, sir. One participant has raised his hand. You can unmute and ask the question.
Yeah, thank you. Please.
Okay. Sir, I have a question regarding the hybrid microgrid configuration. So,
Yeah.
like, how do you decide, like, on which side, whether, like, on which side we connect the wind generator? Whether, like, on what basis do you decide? Like, where do you connect? Like, on the DC side, do you connect it directly to the DC side or to the AC side? So, if you if you actually connect it to the DC side or AC side, like, why do you connect it to AC or DC? Is
I
there like
understand
a,
the question. I understand the question. I will answer it.
yeah,
It
yeah,
depends. Say traditionally, the practice was people believed it till recently, very recently.
yeah,
People believe, all researchers, they believe that a permanent magnet generator is the only solution when it is small and microgrid, a standalone operation. So then, permanent magnet machine will be producing AC, but it is variable voltage, variable frequency AC. So naturally, it needs to be rectified. And when you rectify it, then it becomes DC. In that case, it is better connect it on the DC side. The rectified DC only you are using. Yeah. So that way, permanent magnet generator, if you are using in wind, it is better to connect on the DC side. But then, why I presented this standalone DFIG is that that is the only solution, or that is a major solution which can directly produce AC. You don't need to put it on a DC side and again invert to AC. It can directly come on the DC or AC side, and the cost will be less. So if it is DFIG, then it can be, it should be connected on the AC side, and if it is PMG, it should be connected on the DC side.
okay,